Hi, and welcome to Dr. V's AP Chemistry webcast. Today, the focus is voltaic cells, one of my favorite topics. I love electrochemistry, if you didn't know that already. I wanted to give a special shout out to Dylan, Will, Aiden, and Tal, who helped me put this presentation together, and they did a really good job. None of them are here today, but I've got Henry here with me to talk about voltaic cells with you. All right, so the objectives for today, what I'd like to accomplish. Let's review the main features of voltaic cells. You need to know what happens at the anode, at the cathode. You need to know the role of the salt bridge. You need to be able to calculate the maximum voltage produced by this particular cell. I should mention that sometimes voltaic cells are referred to as galvanic cells. The terms are interchangeable. And we'll complete a practice problem. All right, so let's go on and talk about a half cell. All right, we have a half cell for a half reaction. All right, so what we mean here is that we have an electrode, usually it's a metal electrode, immersed in a solution of its own ions. So we actually have a picture of that here. Okay, and that's probably your easiest way to put a half cell together. It does take two half cells to put together an entire voltaic cell. We have to have a place for oxidation and a place for reduction. One of the electrodes in any voltaic cell is called the anode. And this is where the oxidation process occurs. So if we think about it just in general terms, the metal is making metal cations and releasing however many electrons it needs for the charge of the metal cation that it's making. So you really need to know that oxidation occurs at the anode, right? By convention, the anode is considered to be the negative electrode. Now, the College Board is de-emphasizing that particular piece about the signs that go with it. On the other hand, when you have a battery, a commercially available battery, the negative terminal of your battery either is the anode or is connected to the anode. I don't think there's anything wrong with knowing that. All right, and sometimes it can be hard to keep all these definitions straight. Any tips, Henry?
Well, there's a little mnemonic device. At the anode, there's oxidation, so that if you take the first two letters of one, that's an-ox.
Right, so that can be a really helpful way to remember it. There's just so many definitions in this unit. I use these mnemonics all the time. Every time I teach electrochemistry, I'm constantly saying these things to myself. All right, now the other electrode in the cell is called the cathode. And the cathode is where reduction half reactions are occurring. Reduction is a gain of electrons. So you can think about it as metal cations are gaining electrons that come to them, and they're depositing as metal atoms on the electrode. By convention, the cathode is considered to be the positive electrode. So in your battery, the positive terminal either is the cathode or is connected to the cathode. Now again, keeping all of this straight can be tricky, right?
So we can remember, if reduction happens at the cathode, we can take the first three letters of those, and that spells out red cat.
And again, if that helps you to remember it, that's very useful. So we have all kinds of mnemonics in this unit. Anox, red cat, oil rig, oxidation is loss, reduction is gain. If you can remember those mnemonics, you can actually work through a lot of your electrochemistry problems right there.
And you may think mnemonics are silly, which is maybe fair to some extent, but on the AP exam, if a mnemonic saves you 10 seconds of considering, then that might be the difference between getting a point and not. So
I'm not a big mnemonic user in general, except in this unit. In this unit, I rely on them very heavily because keeping all the definitions straight can be a little tricky. Let's talk about a diagram of a voltaic cell. So we have a zinc half cell, we have a copper half cell. You'll notice they're both in solutions containing their same ion. So the zinc anode is in the zinc nitrate solution. The copper cathode is in a copper 2 nitrate solution. All right. Electrons travel through the wire from the anode to the cathode. That is true in all electrochemical cells. They travel from the anode to the cathode through the wire. Make sure you state that they're going through the wire. What's going to happen is, since oxidation occurs at the anode and you're taking your metal and you're making metal ions, the anode is going to get less massive as the cell is running, right? So it's going to have less and less mass. Now you want to be careful about your terminology there. You don't want to say it gets smaller. It's not simply a volume effect. It's not like it's, getting denser. You're literally taking atoms and turning them into ions that are in solution. So there's fewer metal atoms on it. So you have to say it's less massive. Be careful there. Right? Similarly, the cathode is going to get more massive as the cell is progressing. The metal cations are going to grab electrons as they're traveling through the wire, and they're going to deposit as metal atoms on the cathode.
And often in AP exam problems, the one clue you'll have as to where the anode and the cathode are are the mass changes that accompany them.
Right.
So
That's
make
actually
sure.
not uncommon in the free response questions that you need to use that information. The salt bridge is the other important component of the Voltaic cell that we haven't talked about yet. And what the salt bridge does is allow ions to migrate so that we can maintain a charge balance as the cell runs. Otherwise, you get a buildup of positive charge in the anode compartment, and you're losing positive charge, in the cathode compartment, and you wouldn't have a complete path. You don't have a complete circuit. And so the salt bridge really allows that to happen. The ions move through the salt bridge. Right. Now, in AP, we do expect that students are going to be able to tell us how the ions are moving through the salt bridge. So you need to know that anions are going to enter into the anode compartment, and cations are going to enter into the cathode compartment. Right. So as you're making more positive ions in your anode compartment, you need more negative ions to keep the charge balanced. And as you're using up your cations in the cathode compartment, you need more to replace them. All right. So you really are expected to be able to state that. There have been questions where you actually had to draw that, what was happening in the salt bridge.
And if it ever comes up that you need to construct a voltaic cell, just remember that if you're going to choose ions to put in the salt bridge, whatever salt you're using, make sure they're non-reactive so that you don't screw something up.
Right. You don't want, precipitates forming
Right.
Between the solutions in your cathode compartment and, what's in the salt bridge, or that it's going to be something that's going to react with the electrodes, because that's going to change all your concentrations in a way you weren't anticipating and affect your cell voltages. So that can be a non-trivial concern.
Right.
Now, the other thing we need to talk about is calculating the cell voltage. What's the maximum voltage I could get from a combination of two different half cells? And for this, we often use standard reduction potentials, which are listed here. They've been measured, they've been tabulated. They're all relative numbers. They're relative to the standard hydrogen electrode, which is given a voltage, a standard reduction potential of 0. All right, it's a relative scale.
Right. And that's a big table there. On the AP exam, they'll generally just give you the values you'll need for that problem, but your
Right.
teacher might give you the whole table, so you
Yeah.
should know it.
I usually give the whole table. I prefer it. So what we're seeing here with the standard reduction potential is that we're measuring relative tendencies to undergo reduction. If reduction is something that occurs readily for a particular half reaction, it's going to have a positive number, and if it doesn't occur readily, it's going to have a less positive number, maybe even negative. It's all relative numbers to the hydrogen electrode. All right, so you find your two half reactions here, and the one with the higher E0 value will stay as a reduction half reaction. All right, it's got the greater tendency, and it's going to win that tug of war. And the reaction with the lower reduction potential won't occur as reduction. Notice they're all written as reduction half reactions. It's going to undergo oxidation, right? They both have the tendency to do them both, the ability to do both. It's better usually one way than the other. One of the reactions is going to win. And so the reaction that's got the lower E0 value, the less positive E0 value, we have to flip it to write it as an oxidation half reaction, and the sign of E0 will change, because what we're really doing is writing it now as an oxidation potential. All right. Another visual to help you kind of keep this in mind. So the more likely something is to reduce, the higher up we tend to write it in these potentials, but do check the numbers. Don't just go by position. That's actually, it can be a place to trip you up. So fluorine has a very high reduction potential and tends to do that very readily, whereas lithium does not have a very high reduction potential. It's actually quite negative. So when fluorine undergoes reduction, it makes it possible for, say, lithium ions here to undergo the oxidation potential of the oxidation half reaction. So we would say that fluorine is a strong oxidizing agent. It facilitates the other species undergoing oxidation. Similarly, because lithium oxidizes quite readily, it makes it possible for the fluorine to reduce. And so we say that lithium here would be a reducing agent. It makes it possible for that to happen. You can't have oxidation without reduction here, and so they kind of go together. The College Board has de-emphasized this term of the oxidizing agent and the reducing agent, so it's unlikely you'll have class exams questions on this, but it could show up. Okay, so let's actually go on and do a classic problem, a very typical problem you might get about voltaic cells. A voltaic cell is constructed from a half cell containing nickel and nickel 2 ions, and whatever the counter ions are that we're not paying attention to, and a silver ion half cell. So we're sort of introducing line notation here a little bit. So what we want to do is sketch the cell, showing the direction of the electron flow in the cell. We want to identify the anode and the cathode. We want to write out the net equation for this voltaic cell and calculate Ecell. Now, we're not necessarily going to do this all in this sequence. We're going to do it in the sequence that makes sense to us. What I do recommend you do, try to do this on your own. Can you put this together? Can you identify the anode and the cathode and find Ecell on your own? And then come back and see how your answer compares to what we were doing. Okay, so, all right, we're going to start with the half reactions. All right, silver ion undergoing reduction has a standard reduction potential of 0.80 volts. You can look that up on your table, which you'd have, or you'd have access to these equations. All right, nickel 2 ion, making nickel metal, is a 2-electron process, and it's got a standard reduction potential of minus 0.28 volts. So the one that's got the more positive E0 value stays as reduction. We'll just keep it as written. But the nickel half reaction has actually a negative reduction potential, so it's more likely to undergo oxidation. So what do we have to do? Flip it and change the sign. Okay, so we'll do just that. All right, and then to find the overall balanced equation, we do need to have conservation of mass and charge. And if you need to work on balancing redox reactions, we have a whole webcast just on that. But I have to have 2 electrons gained in my reduction step and 2 electrons lost in my oxidation step. I shouldn't have any electrons left in my balanced equation. The other thing we're going to do is add up our E0 values now that we've flipped our other equation. All right, and so we're going to add everything up, and we have our overall balanced equation in Ecell. Now, typically when I teach students how to do this, I do my balancing the equations with calculating Ecell like side by side, just as I've done it here, because usually you're asked to do these problems together. You know, they kind of go together. You can calculate Ecell, obviously, without writing out the balanced equation. All right, one thing that's very important that I have to point out, E0 values are not multiplied by coefficients. So we had to multiply the silver half reaction by 2 in order to make the electrons cancel. But I do not multiply the E0 value by 2. Right? It is an intensive property. The way the volt is defined already takes care of that. So don't make that very, very common mistake.
There is a situation where you'll need to change E0 values because of concentration or temperature variances, but that's covered under the Nernst equation, which is a separate topic.
Yeah.
Generally, on the AP exam, for instance, that'll be talked about as a separate problem or a separate section of the problem from what we're doing here.
Right.
So don't worry about it.
Right. The other thing is that this is the maximum voltage that the battery, this voltaic cell, could produce. So the Nernst equation actually tells us that this is going to go down over time, but that's the maximum voltage we could get, assuming we're at standard conditions, which we didn't mention with our standard reduction potentials, that we're at 1 molar concentration, so we're at 25 degrees Celsius. If there's a gas involved in any of your half reactions, that it's at 1 atmosphere, and if any of those conditions change, the reaction will change in terms of its cell voltage. But right now, we just want to get the maximum voltage. Usually that's what you're asked to find, at least in a problem like this. The last thing we want to do is put together a diagram. Now, we already have the balanced equation. We know that the silver was undergoing reduction, and reduction occurs at the cathode. And we had the nickel half cell ended up being the one we had to flip to be oxidation. Oxidation?
Anode. At
the anode. So we can actually put all of that together. All right, so we have our silver half cells, we have our nickel half cells, we have the salt bridge. Note that the salt bridge, the U tube of that, is actually in contact with the solution. That's kind of important. We have our external wire connecting the 2 electrodes. We're going to force the electrons to move through the wire. That's really the whole point of setting up the cells this way. All right, so the electrons travel from the anode to the cathode. So that's the nickel to the silver. Right, we have the balanced equation, so we know nickel is the anode, it's undergoing oxidation. Silver is the cathode, it's the one we had to flip. Sorry, I said that wrong. It's the one we didn't flip. The silver is the cathode, the nickel is the anode. We've got our overall balanced equation, and then the ions move through the salt bridge. All right, and so I think that's a pretty comprehensive overview of voltaic cells. I think we're in pretty good shape.
I think so too.
Okay, I think we'll stop here.